Hello everyone, good evening. Here we shall solve some KCET previous year questions in the chapter atoms. Uh, any steps of the solution for us to understand or any doubts we have, let us in the comments. In any other chapter of physics, it will more difficulty to mention the name of the chapter in the comments. We shall give more clarity on it. Even more questions on that chapter. Also, some important homework questions on every chapter based on the previous year case included in the Sapience education. So please install our Sapience education application, which link has been provided in this video. So the first question, it is told solar spectrum is an example of. Solar spectrum is an example of line absorption. Line absorption. So option B is the correct. Question number 2 is told the ratio of minimum wavelengths of Lyman and Balmer series. So minimum wavelength means it corresponds to the highest energy. Minimum wavelength corresponds to the highest energy. The highest energy of transition for Lyman, highest energy transition is n is equal to infinity to n. And for Balmer series, the highest energy of transition will be from n equal to infinity to n equal to so for Lyman series, let's say this wavelength is lambda 1, for Balmer series which is lambda 2. So therefore we have to find lambda 1 by now we know that hc by lambda 1, that will be equal to hc by lambda 1, that is 13.6 electron volt, 1 by n1 square, 1 by n1 square minus 1 by n2 square. So this is 1 by 1 minus 1 by infinity 0. Therefore lambda 1 will be equal to hc by 13.6 electron volt. So electron volt means I can write 1.6 into 10 power minus. And hc you can write that is equal to 1242 nanometer. It is 1242 nanometer electron volt. So therefore lambda 1 I can also say that is equal to hc, that is 1242 divided by 13.6. This is in electron volt, so this much nanometer. And similarly lambda 2, that is hc by lambda 2, that is 13.6 electron volt into 1 by 2 2, that is equal to HC 4HC by 30.6, that is equal to 4 into 122 divided by 13 nanometer. Therefore, lambda 1, this is equal to 4 times of lambda 1. So lambda 1, this will be equal to lambda 1 by 4 lambda 1 equal to 0.25. And D is the correct answer. And in question number 3, it is told hydrogen atom does not emit X-rays. Hydrogen atom does not emit X-rays because X-rays will be emitted when so X-rays are emitted when in any atom one of the electron is ionized, means one of the electron goes outside of the atom, hole is created in that place. So when some electron in the higher energy level will come to fill that hole, then one X-ray photon is, so X-ray not emitted by hydrogen atom since it contains only a single electron. Contains only a single electron. Option C is the correct answer. Question number 4, it is told in Ruby laser the stimulated emission is due to transition from is due to the transition from a metastable state to the ground state. So option C is the correct answer. Question number 5 told that the spectral series of the hydrogen atom lies in the visible region of the electromagnetic spectrum. Spectral series that lies in the visible region of the electromagnetic spectrum, the Balmer series. And B is the. Then question number 6 is told continuous emission spectrum is produced by incandescent electric lamp, mercury vapor, sodium vapor, the sun. So here continuous emission spectrum is produced by an incandescent electric lamp. Incandescent electric. Since mercury vapor lamp, sodium vapor lamp, and the sun, all of these three will give the line emission spectrum. So mercury vapor lamp, sodium vapor lamp, and sun will emit line emission spectrum. So only the incandescent electric lamp will emit the continuous emission. Option A is the correct answer. Question number 7, it is told hydrogen atom from excited state comes to the ground state by emitting a photon of wavelength lambda. If R is the Rydberg constant, principal quantum number n of the excited state. So principal quantum number of the excited state is supposed. So it comes. So from this excited state, one electron comes to the ground state, which is at n, then it will emit a photon of wavelength lambda. If r is the Rydberg constant, principal quantum number n of the excited state is 1. So here we know that the wave number is nu bar, which is 1 by lambda, that is equals to rz square into 1 by n1 square minus 1 by n2 square. So here n is obviously more than 1, so 1 by n should be less than. So therefore, we can say 1 by lambda, that is equal to r into 1 minus 1. So therefore 1 minus 1 by n square, that is equals to 1 by lambda r. 1 by n square, that is equal to 1 minus 1 by lambda. For 1 by n square, that is equal to lambda r minus 1 by lambda r. So n will be equal to square root of lambda r by lambda r minus. So option A is the. Then question number 8, it is told spectrum of an oil flame is an example for this type of spectrum. Spectrum of an oil flame. Spectrum of an oil flame. Spectrum of an oil flame is an example for continuous emission spectrum. An example. Since why it will emit light of all wavelengths. Its emission will have all the wavelengths. So it is a continuous emission. So it is option B is the. Then question number 9, it is told an electron is moving in an orbit of a hydrogen atom. Electron is moving in an orbit of a hydrogen atom, from which there can be a maximum of 6 transitions. The electron is moving in an orbit of a hydrogen atom, from which there can be a maximum of 6 transitions. An electron is moving in an orbit of another hydrogen atom, from which there can be a maximum of 3 transitions. The electron is moving in another hydrogen where it can have maximum 3 transitions. The ratio of the velocity of the electron in these two orbits. So maximum number of transitions therefore the maximum number of transitions or the maximum number of spectral lines due to the transition of the electron from higher orbit to the lower orbit. Due to the transition of an electron from from an energy level n, from an energy level n to the ground state, means to n is equal to 1, which is the ground state. That is given as n into n minus 1 by 2. N into n minus 1 by 2. So here, so suppose if it goes from n is equal to n to n is equal to 1, then the number of possible transitions that can be made, that will be equal to n into n minus 1 by 2. So here the number of transitions for the first case is capital N is equal to 6 here, and for this electron that is equal to 3. Therefore n into n minus 1 by 2, that is equal to 6. It means that n into n minus 1 is equal to 12. So therefore n square minus n square, that is equal to 0. So n minus 4 into n plus 3, that is equal to n should be equal to 4 in the first case. So it means here the electron is in the fourth energy level, in the fourth shell. And in the second case, the number of spectral lines, that is equal to 3. Therefore n into n minus 1 by 2, that is equal to 3. Therefore n square minus n minus 6, that is equal to 0. So therefore n minus 3 into n plus 2, that is equal to 0. So therefore n should be equal to 3. N should be equal to 3. So here in the second case, the electron is in the third energy level. Therefore in the first case n is equal to 4, and in the second case n is the velocity of the electron. Now therefore we know that the velocity of the electron in an orbit, velocity of the electron in an orbit, that is given as that v in the velocity v in the nth shell is inversely proportional to n. Since by the energy in the nth orbit, that is proportional to 1 by n square. So therefore, if the kinetic energy is inversely proportional to n square, so the velocity in the nth orbit should be inversely proportional to n. Therefore, the ratio velocity of the electrons in these two orbits. So means we have to find v4 and v3. It means that will be 1 by 4 by 1 by 3, that is 3 by 4. Option D is the correct answer. Then in question number 10, it is called mu1 is the frequency of the series limit of Lyman series, and mu2 is the frequency of the first line of Lyman series, and mu3 is the frequency of the series limit of the Lyman series. Then what is the relation in between these three frequencies? So we can say that h1, that is the frequency of the series limit of Lyman series, that will be equal to 13.6 electron volt into the series limit. So that is going from infinity to 1, that is 1 by 1 square minus 30. Therefore mu1 that is 13.6 electron volt, that by this Planck's constant. And then the frequency in the first line of Lyman h mu 2, that is 13.6, that is going from n is equal to 2 to n is equal to 1. So this is 1 minus 1 by 4, that is equal to 3 by 4. So mu 2, that is equal to 13.6 electron volt, with 3 by 8. Mu 3 is the frequency of the series limit of the Balmer series. So that will be equal to h mu 3 will be equal to 13.6 electron volt. So 1 by series limit of the Balmer series. So this will go from infinity to 2. So therefore mu 3, that is equal to 13.6 electron by 4h. Therefore here you can see that mu 2, that is equal to 3 by 4 into mu 1, and mu 3, that is equal to 2 by 3. 2 by 3. I can say this is equal to mu 1 by 4. So mu 1 minus mu 2, that is equal to mu 1 minus 3 by 4 mu 1, that is equal to 1 by 4, that is equal to mu 3. Therefore mu 1 minus mu 2, that is equal to mu 3. And A is the correct answer. Then in question number 11, it is told that the de Broglie wavelength of the electron in the ground state of the hydrogen atom is. The de Broglie wavelength of the electron in the ground state of the hydrogen atom. Radius of the first orbit of the hydrogen atom is 0.53 angstrom. De Broglie wavelength of the electron ground state of the. So de Broglie wavelength, that is equal to h by mv. So for the ground state, we know that mvr is equal to nh h by 2 pi. Radius of the first orbit is 0.53. I can say mv, that is equal to h by 2 pi r. This you can write h by 2 pi r to 2 pi r. Lambda will be equal to 2 pi r. 2 pi 2 into 3.14 into the radius, that is 0.53, which is approximately 3.33. Approximately 3.33 angstrom. So option B is the correct answer. It means that the de Broglie wavelength is same as the perimeter of the first orbit. The de Broglie wavelength is same as the circumference of the first orbit. Then question number 12, it is told that Rutherford's atomic model could account for stability of atoms, origin of spectra, positively charged central core of an atom, concept of stationary orbits. So the Rutherford's atomic model could account for the positively charged central core of an atom, which he called as the nucleus. Since C is the correct. Then question number 13 shows that when an electron jumps from n is equal to 2 n is equal to 4, from then wavelength of the radiation absorbed will be, so the wavelength of radiation absorbed, so 1 by lambda is equal to r into 1 by n1 square minus 1 by n2 square. So 1 by lambda, that will be equal to r into 1 by 4 minus 1 by 6. This will be equal to r into same is 16, so the 16 minus 1. So 1 by lambda, that is equal to 3r by 16. Therefore, the wavelength will be equal to 16 by 3r. Option A is the correct answer. Question number 14. Question number 14, it is told the ratio of the minimum wavelength of Lyman and Balmer series. So for minimum wavelength corresponds to the highest energy of transition. So it means that for Lyman, the highest energy of transition in Lyman will be when the electron goes from n equals to infinity to n equal to 1. And in the Balmer series, the highest energy of transition will happen when the electron goes from n is equal to infinity to n is equal to 2. So therefore, let's suppose the minimum wavelength in the Lyman series is lambda 1 and the minimum wavelength in Balmer series is lambda 2. Therefore, I can say 1 by lambda 1, that is equals to r into 1 by 1 square minus 1 by infinity square, and 1 by lambda 2 also, that is equal to r into 1 by 2 square minus 1 by infinity. Therefore, 1 by lambda 1, that is equal to r, and 1 by lambda 2, that is equals to r by 4. Therefore, lambda 1 by r, lambda 2, that is equal to 4 by r, is equal to 4 lambda 1. So therefore, the required ratio of the minimum wavelengths in Lyman and Balmer series, so that is lambda 1 by lambda 2, lambda 1 by 4 lambda 1, that is 1 by 4, which is equal to 0.2. And B is the correct. Question number 15 is told if n is the orbit number of the electron in a hydrogen atom, the correct statement among the following: n is the orbit number of hydrogen atom. Electron energy increases as n increases. The energy of the electron. So here we know that the energy of the nth orbit, that is given as minus 13.6 electron volt per square. It means that with increasing n, 1 by n will decrease, but minus 1 by n square. 1 by n square will decrease, but minus 1 by n square will increase. So the electron energy increases as n. Option A is the correct answer. Option B, it is told hydrogen emits infrared rays for the electron transition. N is equal to infinity to n is equal to 1 corresponds to the highest energy of the transition in the Lyman, and Lyman series is in the ultraviolet region. So hydrogen will emit UV rays, ultraviolet rays. It goes from n equal to infinity to n equal to 1. Electron energy is 0 for n is equal to 1. No, it is 2. And electron energy varies as n is equal to 4. A on the is the correct. Then in a ruby laser, the color of the laser light is due to chromium. Color of the laser light in a ruby laser is due to chromium. Then the spectrum of sunlight is an example for number 17. It is told the spectrum of sunlight is an example for band emission spectrum, line emission spectrum, and continuous emissions. Question number 17 is told that spectrum of sunlight is an example for line emission spectrum. And B is the correct. In question number 18, it is told in hydrogen atom, electron excites from ground state to higher energy state. Electron excites from the ground state means n is equal to 1 to higher energy state n, and its orbital velocity is to 1/3 of its initial. So here the orbital velocity Vn, that is equals to 1/3 of the V1, means the velocity in the first orbit, means in the ground state. The radius of the orbit in the ground state is r. The radius of the orbit in the ground state is r. Then how much is then the radius of the orbit in that higher energy state Rn? That is okay. So now we know that Vn, the velocity of the electron in orbital velocity of an electron in an hydrogen atom is inversely proportional to n. So V1, that will be equal to some V0 by 1. Let's say that is V0. So Vn will be also equal to V0 by 1. Where V0, I am saying it is some constant of proportionality. So this is equal to V0 by 3, it is told. So therefore it means that n is equal to 3. And we know that the radius of the nth orbit, that is proportional to n square. So the radius of the first orbit, that will be equal to some constant a0 into 1 square, so which is equal to r. So a0 is r. Therefore the radius of that nth orbit, that is equal to n square into a0, equal to n square r. Here n is 3, so therefore it will be 3 square into r, that is 9r. So option D is the correct answer. In question number 19, it is told that the ratio of the magnetic dipole moment m to the angular momentum of the electron in the first orbit of hydrogen atom. So the magnetic dipole moment, that is given as the electric current into the area. Electric current, that is charge by time. The time period of revolution is 2 pi r by v. 2 pi r by v into, so current into the area, that is pi r square, and the angular momentum, that is equal to mvr. So pi and pi will cancel, r will cancel, so vr will also cancel, so that is equal to E by 2m. So it is equal to E by 2m. So option A is the correct answer. Question number 20 is told that pick out the correct statement from the following. Mercury vapor lamp produces line emission spectrum, and oil flame produces line emission spectrum. Oil flame will produce a continuous emission spectrum. Band spectrum helps us to study molecular structure. Sunlight spectrum is an example for line absorption spectrum. So here the only incorrect statement is option B. So A, C and D are correct options. A, C and D are correct statements. Here only option B is incorrect statement. So here A, C and D are correct options. Then question number 21, it is told light emitted during the de-excitation of electron from n equal to 3 to n is equal to 2 when incident on a matter. So the electron goes from n is equal to 3 to n is equal to 2. So it will emit some light photons. Some light photons will be emitted when incident on a metal. Photoelectrons are just emitted from that so when this light emitted is incident on some metal, then some photoelectrons are ejected, are just emitted from that metal. In which of the following de-excitations, photoelectric effect is not possible? So here the energy of the photon that is emitted, that should be equal to the work function of the metal, is phi naught. That should be equal to the energy of transition from n is equal to 3 to n is equal to 2. That is equal to 13.6 electron volt into 1 by 2 square minus 1 by will be equal to h nu, that is equal to phi naught equal to 13.6 into 4 minus 1 by 9. Therefore h nu, that is phi naught, that is equal to 36 minus 4, 5. So 5 into 0.6 divided by 36. Much electron volt. So now, which of the following de-excitation photoelectric effect is? So now, therefore, the first option, from n is equal to 2 to n is equal to 1, the energy of the photons that will be produced, that will be equal to 10.6 into 1 by 1 square minus 1 by 4, 1 by 2 square electron volt. That is equal to 1 by 4, so that is 3 by 4 into 13.6 electron volt. So 5 by 36 is approximately so this I can write 27 by 36. 27 by 36 into 13.6 electron volt. So which is obviously more than the work function of the metal. So here photoelectric effect will happen. Option B, here the energy of the photon, that is 13.6 by 1 square minus 1 3 square, since it is going from n equal to 3 to n equal to 1, that is equal to 13.6 into 9, so 8 by 9, that is equal to 13.6 into 32 by 36 electron volt. This is obviously more than the work function. the work function is 5 by 36 into 13.6, and so in case B also photoelectric effect will happen. Then in option C, the energy of the photon, that is 13.6 into 1 by 2 square minus 1 by 5 square, since it is going from n equal to 5 to n is equal to 2. So that is equal to 13.6 into, this is 25 4, 25 4 is 100, and 25 minus 4, that is 21 by 100. Now 5 by 36, 5 by 36 is approximately equal to 0.139, 0.139 into 13. But this is 0.21, is obviously more. And in option D is going from n equal to 4 to n is equal to 3. So here the energy of the photon, that is 13.6 electron volt into 1 by 3 square minus 1 by 4 square. 9, 16, 144, 9, and this is 15 minus 7 by 144 to 13. And 5 by 36 means I can write this is 144 and 20 by 144, which is obviously more than 7 by 144. So therefore this value is less than the work function finite. So therefore in the case D, in the transition, in the dxi expression from n equal to 4 to n equal to 3, here in this case the photon which will be emitted, that will not cause the photoelectric effect in this matter. And D is the correct answer. And in question number 22, it is to ionization energy of an electron in the ground state of helium atom. Ionization energy in the ground state means n is equal to 1 is 24.6 electron volt. The ionization, the energy required to remove both the electrons ground state of the helium. Ionization energy ground state, that will be equal to 13.6 electron volt into z square by n square. Z square is the atomic number of helium, He. Therefore this will be 4 into 30. So here the first ionization energy, that is equal to 24.6 electron volt. So the second ionization energy the helium atom, since why it is in the He plus state, means it is a hydrogen like species, So here the formula 13.6 z square by n square can be applied. So the ionization energy is 13.6 z square by n square. That can be applied only if it is a hydrogen like species. Since the Bohr's model, Bohr's atomic model can be applied only for hydrogen light. So the second ionization energy, that will be equal to 13.6 into z square, that is 2 square by n square. N is equal to 1 for the ground state. So this is equal to 4 into 13.6 electron volt. So that is equal to 4 6 24, 52, so 54.4 electron volt. So now, therefore, the energy required, therefore, the total energy required to remove both the electrons, energy required to remove both the electrons is the sum of the two ionization energies. It is equal to 24.6 plus 54.4 electron volt. So that will be equal to, that is 10 plus 4, 8, 9, 79 electron volt. Option B is the correct answer. B is the correct answer. So hope you have understood the solutions of all these 22 questions. So here we shall end the first part of this video on the previous year KCET questions of the chapter of atoms. So any doubts if you have, then please write us in the comments section. Please install our Sapience education application, where we shall upload some important previous year KCET questions on every chapter, which shall be helpful for your KCET. Thank you, everyone.